Hey guys, Packetuse here, back again finally with another video on programming for the ZX Spectrum. Yeah, I promised to release this video like 3 or 4 years ago, but life's got its own way, so I couldn't get back to it back at the time, but hopefully this time I'll be more consistent, because in this series of videos I plan on covering the development environment, the ZX Spectrum memory layout and video RAM, which we'll be covering today, the Z80 assembly instructions and registers, and the ZX Spectrum ports that we'll use for like changing the border color, whatever else, and outputting sound, and all that kind of stuff. Also, some of the most useful graphical routines, like calculating the address of a line below that you are currently on, and doing it as fast as possible. And also some graphic effects, and making music in Vortex Tracker, because what kind of demo can you make if you don't have any music in it and no graphics in it? And whatever else it might be, just let's see how it goes, and just yeah. So let's go. The first part is memory layout basics and the development environment. The ZX Spectrum memory layout. The 48K ZX Spectrum has 8 chips of 16 kilobits of slow RAM, the so-called contented memory, and 8 chips of 32 kilobits of fast RAM. The slow RAM can be accessed both by the ULA and the CPU, and the ULA has priority because it renders the image on the TV. That's why this memory is considered slow, because when the ULA is drawing the image on your TV, the processor must be stopped. In fact, on the ZX80 there was some kind of a fast mode that allowed heavy calculations and allowed to do them fast, but it turned off the screen while it was calculating. And that was done for the similar reason. The 128K has half its RAM fast and half its RAM slow, and the pages for the fast RAM and slow RAM are mapped a bit different on the +2 and +3, so you can't create quite a universal application. You have to either write a lot of movable code or just write separate applications for the +2, +3 and the 128K. But however, there was a series of Russian Spectrum clones called Pentagon. I use one myself actually, and they have a unified memory field. That means all RAM is fast on those. That's why Pentagons are very much loved by the demo makers of the day. The Z80 can address up to 64 kilobytes of RAM, and that address space is used in whole on the ZX Spectrum 48 without any paging. In the very top of the address space, the ROM is located. Right after that, at 16384 or 4000 hexadecimal, begins the display data, and it's organized in quite a weird way, but we'll talk about it later. Then, there are also 728 bytes of attribute data for it at 5800 hexadecimal, and that's basically what defines the colors on your screen. Up next, there are some system variables, printer buffer, and etc. at 5B00 hexadecimal, and the rest is free for your programs up until FF58 hexadecimal, where the stack is located. When you use the command clear in BASIC, you're basically changing the starting point of that block, so your program would not collide with the stack and whatever else BASIC might need. So yeah. Talking about the display memory, if you look at the address 4000 hexadecimal, you will see that only bit A14 is on, and those first 3 bits are actually what defines the base address of the screen memory. But the simple things stop right there. The next 2 bits are the number of the third of the screen. The ZX Spectrum display is split in 3 equal parts vertically, so those 2 bits define the third you are going to use. The next 3 are the pixel Y position within the character. Yes, the ZX Spectrum acts as a terminal, so everything related to the graphics is done within character spots, and well, basically just like a terminal with a custom font. This will define the vertical position within the character spot you are currently in. And the next 3 define the number of character line within the third. Every character line has 32 characters Every character line is 32 characters horizontally and 8 pixels vertically. Every character is 8 by 8 pixels. And the next 5 is the number of characters within the line. So for example, if we write a 255, that is all bits on, in a byte to the base address 16384, we'll see that the top left character has its top left line black. That means all the bits are on in this address. However, if you want to move this black line a pixel lower, then you just need to add 1 to bits A8 to A10. That will be the second line of the character, and you see the line has moved down a bit. And you just add 1 to the bits A8 to A10, which is decimal 256 or 2 power 8. Now let's move this line even further 8 pixels down. How we do it? Well, you guess it, we just add a line of characters to there. That is bits A5 to A7. So just add 32 or 2 power 5, and our line has moved 8 pixels down. So let's take a moment and create a program in BASIC to write an underlined hello world. We'll start off with print hello world as usual. This will display our greeting at the top left of the display, pretty much your usual basic command. Then we'll make a loop over I from 0 to 10. That gives us 11 iterations, and the number of characters in hello world is exactly 11. These 11 times we'll be writing 85 to the address 16416 plus I. Why 16416 is because that is the beginning of the second line of characters and the topmost line of characters in the top third of the display, like we did earlier. Simple as that. And why 85? It's because I don't like solid underlines, and 85 basically is 0 and 1 alternating. Then we should finish the program with a matching next I to close the loop. And if we try to run it, you get this neat underlined hello world. Brilliant, it works. However, it works with a bit of a visible lag. That's why we should program in assembly, because BASIC is like 16 times slower than assembly. Yeah, so let's write a program that does just that to test our development setup. But before, let's talk about attribute area. It's located right after the display memory, and it has 768 bytes, where every byte is for a 8 by 8 pixel block on the display. It basically defines the colors for that 8 by 8 pixel block. The first 3 bits are the ink color. This color will be applied to the pixels that have 1s in them. The next 3 are the paper color. That color will be applied to the bits that have 0s in them. The next bit is the bright bit, which means that the colors defined in the previous 6 bits will be a bit brighter. And the next one is the flash bit, which will make the paper and ink color change around every couple of interrupts. And basically, that's what happens when you try to use more than 2 colors within an 8 by 8 pixel block. However, really professional artists can deliver images that make this effect really unnoticeable. So, let's move on to setting up the development environment. You're not gonna need much disk space, neither you'll need much tools, and I'll provide all the links down below in the video description. Of course, this is just the workflow I use, so you might want different tools or different ways of doing things, so share them in the comments so others would know. To write programs you'll need a text editor, and that's where Sublime Text really shines with the Z80 mode for it. Autocomplete and syntax highlighting just brilliant. And in order to compile what you've written, you're gonna need an assembler, and I prefer SJS Plus because it has Lua support and many other powerful features, and is overall cool and cross-platform. It can output binary files for use on tapes, or emulator snapshots for quick testing, as well as even TR-DOS disk images. and that's a big plus for us. We're going to automate a lot of things so that we don't have to use our emulator every now and then. And for emulating the Spectrum on my PC, so I don't have to run to the real Pentagon for every test, I use Fuse. And Fuse stands for Free Unix Spectrum Emulator, so I'm not sure if that exists for Windows, but hey, there are millions of others for Windows, like Unreal Spec, Spectaculator, I'm using just loads of them. So choose the one you like, they're almost the same. And to edit the tapes and disk images, I use MCTRD, which is also cross-platform and compact. Windows, Linux and Mac, it's got you covered everywhere. To edit the graphics, I use a bit of an older version of ZX Paintbrush. I'm not that good at drawing, so I mostly use this for converting graphics and then correcting them by hand, so it gets the job done for me. But what can demos and games be without any music? So you need a musical editor, and I prefer Pro Tracker on the Pentagon or Vortex Tracker 2 on my PC. Again, this is quite an old version, and there were many of those improved versions of it with MIDI support and all that kind of stuff, but I didn't look into those just yet. And of course, you're gonna need a lot of different tools you use daily on your computer, like Paint.net or Photoshop, Notepad, Excel, all that kind of stuff, just because, yeah, if you're going to write a serious demo, you'll need to pre-calculate a lot of stuff, because the Spectrum is not that quick. It just has a Z80 processor at 3.5 MHz, so really not much CPU time you can use there. So I'll assume that you have enough experience in installing things onto your computer, so let's just go ahead and write the program we made earlier, but in assembly. So here's our development environment. We have a terminal, a folder, and an empty file.
I have a
Terminal.
I have
An empty file. An empty file called underline.asm in our folder, open in the Sublime text editor. So let's go ahead and write a program. Remember, we have to start at address 16416 and write 85 11 times from there. So first, we're going to go ahead and write device ZX Spectrum 128. This is not an assembly instruction, but in fact a compiler directive that's telling the compiler that we're developing for the ZX Spectrum, and specifically the 128 model. The next one is going to be a compiler directive too, and that'll be org 25000. This line tells the compiler that we're going to load this code at address 25000. So basically, there are no labels, functions or whatever in actual machine code. There are only memory addresses. Like, you have an occasional label in your program and it needs to know where it's pointing at. So it needs to know where the start actually is. Let's just add a label there called main. We're not going to be using this label anywhere in our program, but it's a good idea to write your program in a label called main. Okay, so now that we have our main label in place, it's also a good idea to go back to org 25000 and add an instruction jp main, which stands for jump to main. In fact, it might seem useless right now because the main label is just after that instruction, so it's doing nothing. But actually this might be a bit useful, because many people don't realize that the first instruction they have in the file is the first byte that would be output, so they keep on writing instructions and routines above the main procedure, and when they try to load this code and they be like, oh, why doesn't it work? Why does it just crash for some reason, or try doing something else but not do it the way I wanted it? That's simple, because you've put code above the main procedure and basically it's starting from the code you've put there. And if you have this JP main there, it just ignores whatever I might write in between. Like, I might put in a di out, which means disable interrupts and stop until we get next interrupt. So basically, yeah, you see it's a deadlock condition, but this way it'll go there and then just jump over here, and this will never be executed. So yeah. Now within our main block, let's write our first instruction, and that would be loading the number 85 to the processor's accumulator. That would be LD, which stands for load in Z80 assembly, A, comma, 85. So basically we are telling the processor, like, take this number and load it into your register A, which is the accumulator. It's called the accumulator because, like, on a usual calculator, you see, like a non-programmable calculator, you have a display, you type in a number and it instantly appears on the display. You then type an operation, type another number, and then hit equals, and you see the result on that exact display. You don't have separate displays for everything. And the display on a physical calculator is basically the same thing as the accumulator on the Z80. All the operations are done within the accumulator mostly. So, like, if you want to compare a number, you would have to load into the accumulator. All that kind of stuff. So yeah, this will take the number 85 and load it into the accumulator. On the next line, let's load our address 16416 into a pair of registers H and L. Basically, the register H and the register L are separate registers and can be used separately. However, if you need more than one byte, and 16416 is definitely more than 255, which one byte can fit, and that way you have to use a register pair. There are not many register pairs. I can remember that HL is a register pair, BC is a register pair, also SP, but you don't have to change that because it shows the processor where the stack is pointing to. We'll look into that a bit later. Also IX and IY, but those have different uses because, well, basically assembly is writing the code for the hardware itself. You get stuck in the limitations of the hardware very often here. So 16416 would be our first pixel address. Yeah, you see, this is way more than 255. Thus we have to use 2 registers for it. And on the next line, let's load the register B with 11, which is the number of iterations we want to do. So we want 11 bytes to be filled with 85, thus we load 11 there. Now let's put another label and call it underscore loop. I use an underscore to show that this label is not meant to be called directly. It is meant to be called within a loop or within a subroutine inside an outer routine, so I don't just call it directly. So yeah, within the loop we want to load our accumulator to our pixel address. That way we write load again, then add parentheses and HL inside this. Those parentheses tell the compiler that we are not going to use this register right away. So it's not like take this number and load this into this register, but instead we tell the processor take this accumulator and take this value in the register pair HL and consider the register pair HL to contain the memory address and write the contents of the accumulator to that memory address. So basically that's writing into a memory at location 16416, and that would write the number of 85 which we have in our accumulator. Then we'll want to move a byte further by incrementing HL, and there's an operation for that called inc, which stands for increment. That will just add 1 to HL. And now the most complicated part comes, DJNZ underscore loop. DJNZ stands for decrement jump if not 0. This instruction actually performs many things at once. First, it decrements our B register, then checks if it's 0, and if it's not yet 0, it goes to the label we specified here. So that means then that it will go right there, perform all this code, hit this instruction, decrement B, and say, oh, B is now 10, but 10 is still not 0, so let's go ahead and do it over again. Do it over again 11 times, and on the last iteration it says, well, B is 1, decrement once, and B is 0. We don't have to do anything else, so it will just continue with the code we have there. Just on and on, without any jumps. That's very convenient to organize loops that way, but loops are not a great thing on the Z80, and in the next videos you'll see why. And we don't have anything else to do, so we'll just tell it to return. The ret instruction, basically it returns control to whatever routine called our program. In our case we'll be calling this from basic, so this will tell our basic program to continue. Okay, so our program is done, so we have to add another compiler keyword, that will be output. And into quotation marks we add the file name that we want this under. So let's call it underline.binary. Okay, saved it. Now go to the terminal and type in sjasm plus underline.asm, or whatever the name you save this code under. Hit enter. You see, pass 1 complete without any errors, pass 2 complete without any errors, so error 0, warning 0, 14 lines compiled, and that means we're basically done. So, if you were to open this with HexEdit, you would see all this code. If you had an Apple I instead of ZX Spectrum, you would be just typing this in on the monitor and then running this, but the ZX Spectrum is quite a bit different, so let's load this on a tape. Type in mctrd new test tape. That will create an empty tape file over here in our directory. You see, it's 0 bytes. So we have to add our file now. mctrd add underlined binary to test tape. Simple as that. Hit enter, and now you see our tape has become 40 bytes. Which means, if we open that up in the emulator now and have a look at the tape drive, you see we have our underlined bytes here. So let's go ahead and enter basic and write our program. 10 load empty quotes, because we couldn't care less about the file name now. We only have one file on the tape. Code 25,000. With the code keyword we tell the basic that we are trying to load raw machine code and the specified address. Then 20 would be clear screen. 30 would be print hello world, just like we did earlier. And 40 would be randomize USR 25,000. The reason we have to use randomize is because, well, the thing that calls our code is actually the USR keyword, but the designers of the ZX Basic made it in a way that if you don't have its output returned to anything, then this keyword is useless, thus it's considered invalid. So, as we couldn't care less about what the random seed is, it's supposed to be random, we just used randomize. So yeah, and if we try to run this now, and we hit play, oh, the good old sound. And you see, it worked actually pretty nice and pretty fast, even though we were in the contended memory, because 25,000 is within the contended memory of the Spectrum. And if we wanted that even faster, we could have moved this into like somewhere around 32,678. I think that's where the contended memory ends on this 48K. But we're on the 128K right now, so that doesn't apply. And basically now, and well, let that be your home task. If you want, just go ahead and change the program in order to make the underline red on the same white background. Maybe even bright red if you're into that. So, thanks for watching. Please don't forget to like and favorite and subscribe for more ZX Spectrum tutorials. I'll see you guys next time.